This year, UBC UAS was lucky enough to have contributions from one of its largest and most diverse teams in our history. With almost 50 members spread across 4 sub-teams, we were able to innovate in every area with new and exciting ideas. 11 of these members will be attending AUVSI SUAS, and it's time for you to meet them.
Hi, I'm Luke Goldstein. I'm in my 3rd year of integrated engineering. In my 3rd year on the team, I'm the team captain. I oversee all system operations and ensure smooth operations on the flight line.
Hi, I'm Yekta. I'm in my 2nd year in electrical engineering and UBC UAS. As part of the payload team, I make sure that the payload is delivered safely and timely manner.
Hi, I'm Eric McCoolin. I'm in my 2nd year of civil engineering and my 1st year on UBC UAS. I'm on the ground control software team, responsible for the waypoint generation and obstacle avoidance algorithms.
Hi, I'm Wesley Chang, and I'm in my 2nd year of computer engineering. In my 2nd year on the team, I am the software lead. I oversee our software suite and ensure reliable image processing.
Hi, my name is Kirsten May. I just graduated from mechanical engineering. This is my 2nd year on UBC UAS team, and I am part of the payload team. I model and rapid prototype payload mechanisms, and I help ensure that logistics are well organized for the competition.
Hi, I'm Adam at Wally. I'm in my 2nd year in mechanical engineering, and I'm in my 2nd year with UBC UAS. I'm the radio communications mechanical lead, and I ensure that we have a strong structure for our antenna tracking station.
Hi, I'm Garika Sonvi, and I'm in my 3rd year of electrical engineering. This is my 2nd year on the team, and I'm the radio communications electrical lead. My job is to ensure all radio links between the aircraft and ground have been established, and I also oversee the electrical and software development of the antenna tracker.
I'm Grant Anderson, and I'm in my 3rd year of electrical engineering. In my 1st year on the team, I ensure that the antenna tracker can accurately track and turn towards the drone for full functionality.
Hi, my name is Yi Yan. I'm on my 3rd year of computer engineering, and I'm the payload lead who design the payload's hardware and software, and also I ensure the integration between payload software and the ground control software.
Hi, I'm Andy Kwan, and I'm on my final year of electrical engineering. This is also my 5th and final year with UBC UAS. I'm the team's advanced technology advisor, specializing in all systems design and propulsion. I also help lead aircraft, making sure everything runs smoothly, and the safety pilot on the flight line.
This year, UBC UAS has completely redesigned and manufactured a new quadcopter to meet the mission requirements of AUVSI Student Unmanned Aircraft Competition 2019. Condor houses a robust frame with a strong aluminum core used to support an 11-kilogram takeoff weight. The landing gear has been designed to be durable and shock absorbing. The payload consists of the UGV and a Sony A5100. The winch system is designed to allow a safe deployment of the UGV. The loss of any connection will trigger a fail-safe mode, and the aircraft will safely land itself. Camera images will be relayed over a point-to-point network formed over the Ubiquiti bullet transceivers. This 2.4 GHz connection provides long-range telemetry using a directional Yagi antenna on the antenna tracker on the ground. The antenna tracker operates via the Raspberry Pi, controlling 2 Dynamixel motors for yaw and pitch movement. The 2 degrees of freedom are achieved via gears instead of a belt drive in order to reduce slippage and use lighter material. The antenna tracker will follow the UAV using GPS data pulled from Mission Planner.
The new software suite, GCOM V2, takes the provided mission points and obstacles and auto-generates a 3D waypoint mission, which is then uploaded to Mission Planner for execution. GCOM V2 also geotags each image and identifies the characteristic of the detected objects autonomously. Finally, GCOM V2 will send UAV telemetry data and images over to the interops server.
UBC UAS will be attempting all mission tasks this year, excluding imaging off axis and emergent objects. At the moment, all object detection and localization is done manually.
The base aircraft was tested without any payload first. This consisted of 1 hour of manual flights in order to verify all flight characteristics performed as expected. This also includes preliminary tuning and autopilot test flights. The maximum flight envelope was determined and tested by adding more and more weight to the aircraft. Aggressive flight tested the ability of the aircraft to remain stable under load and in high wind environments, or when tight, fast maneuvers needed to be executed, like in an attempt to avoid obstructions. After the aircraft is determined to be safe and controllable in manual and auto flight, while at the full mission weight, the payload was added. Once the payload is mounted, final tuning is able to take place. This initially consists of manual tuning adjustments to allow the pilot as much control of the aircraft as possible. Then, an auto tune is run to dial in the final precision tune. After this, several flights are conducted to ensure smooth and reliable flight. Auto flights verify the autopilot's ability to maintain control of the aircraft with the added weight. Once the payload is well integrated into the aircraft and all flight-related testing and tuning have taken place, payload testing and tuning commences. This is where the images are taken and the airdrop tests are performed. 26 autonomous flights were conducted, with an average manual time of about 10 minutes each. Mission Planner was used to tune the Pixhawk PID, and then Auto-Tune was used to refine the results. Mission Planner was also used for accelerometer, IMU, compass, and manual mode radio calibration.
Waypoint accuracy was tested by flying several autonomous flight paths and comparing log files to waypoint lists. First tests revealed problems of missing up to half of the waypoints due to routing problems. Changes in autopilot settings allowed us to achieve up to 100% waypoint capture with accuracies consistently below 8 feet.
Our obstacle avoidance uses a pathfinding approach based on the famous A-star and L1 algorithms. We have a large suite of unit tests that test a variety of obstacle edge cases and scenarios to ensure that our avoidance algorithms can handle any scenario. This includes preset edge cases as well as a random route/obstacle test generator. These generated routes are verified that they do not collide with other obstacles and double-checked using RGPilot's SITL drone simulator. These tests are run using a continuous integration server and are verified against each code change. Since we take into account the size of the drone and use a fully featured pathfinding algorithm, we trade in potential route efficiency in order to guarantee that all obstacles are avoided. Imaging is done with a high-resolution Sony A5100. With a total of 24 megapixels, we are able to sharply resolve small objects well over 50 meters away. We tested our imaging performance by always testing with a large factor of error. For example, we often took images at a higher altitude than our planned survey path to ensure that we could see the objects at our lower typical altitude, as well as when we have to pass over obstacles. We also used practiced objects that were much smaller than the ones used in previous competitions to ensure that we'd be able to identify any object. Image tests were done in a variety of lighting conditions, including sunny as well as overcast. Our detection and classification task is performed manually by our highly trained ground crew to ensure maximum accuracy. During flight tests, objects differing in letters, colors, and shapes were scattered and then identified using our GCOM V2 IMP interface. Since we knew the location of all objects using a phone, GPS, and compass, we were able to verify that each identified object had the correct characteristics. Out of 39 objects tested, 35 were correctly identified 100%, and all 39 objects had at least one characteristic correct. Our localization system was first heavily unit tested to ensure algorithm correctness across a variety of parameters, such as altitude, location, and aircraft roll. Then, they were tested against real objects during flight tests, and our calculated latitude/longitude values were compared against the true locations given by a phone GPS. 14 objects were tested across several flight tests, and our calculations had an average error of less than 20 feet. We followed an iterative design process for the UGV and UGV deployment system. We modeled our system based on its major physical mechanisms, and then iteratively designed different controls to improve the dropping speed, stability, and controllability. Then we rigidly tested the system to ensure that it's reliable and accurate under different wind conditions. A total of 14 airdrops were attempted, 9 of which the payload survived the landing. The other 5 times were used to make improvements during the iterative design process, including a new winch braking system. On average, the payload has landed within 1.5 meters of the expected target.
UBC UAS conducted 6 mission flight tests throughout the developmental process, with the airdrop module included in the last 3 mission tests. Therefore, we saw gradual improvements to our test flight results. In terms of timeline, we were able to achieve no overtime penalty for 5 of our tests. We captured all waypoints and achieved full autonomous flight without manual takeovers. With an improved waypoint accuracy of 5 to 10 feet, we were able to achieve an average of 97% in autonomous flight points. Using our new navigation algorithm, we were able to avoid all stationary obstacles in the last 2 flight tests, achieving full points in the obstacle avoidance category. Our object recognition suite was able to recognize the majority of characteristics. Furthermore, we obtained an average geolocation accuracy of 6 feet, resulting in an average score of 78% in object detection, classification, and localization. In our last 3 tests, we conducted airdrop. Although our first attempt revealed problems with our winch mechanism, our second and third attempts proved successful, and we were able to drop our rover safely, ending with a 50% score in our last test.
Through rigorous testing of its full systems, the team is confident in its ability to complete the selected tasks successfully.